All right, welcome everyone. If we really want to master advanced electric drives, we've got to get inside the mind of the induction machine. And you know what that means? It means understanding its dynamic behavior. So today, we're going to build the mathematical language we need to do exactly that, deriving the machine's equations right from the ground up. Okay, let's jump right in. At the heart of the induction machine, there's this paradox, the squirrel cage rotor. I mean, look at it. It seems so simple, just a bunch of uniform metal bars. But the physics of this thing produces a beautifully sinusoidal magnetomotive force, which is exactly what we need for smooth operation. So to analyze this, we do something pretty clever. We mathematically replace the physical squirrel cage with an equivalent set of 3 perfect, sinusoidally distributed windings. This is our foundational first step.
So here's our game plan for today. We'll kick things off by setting up the basic framework and our core assumptions. Then, we're going to deconstruct the machine down to its most basic building block, a single phase. From there, we'll build it back up into the complete 3-phase stator. After that, we'll get into the nitty-gritty of calculating the self and mutual inductances. And finally, we'll put all the pieces together into one beautiful, coherent model. All right, Section 1, the modeling framework. Our goal here is actually pretty simple. We want to translate the physical machine into a set of equations we can actually work with. And the key to everything, the absolute key, is understanding how this machine is so meticulously designed to create one very specific thing, a perfect magnetic field in its air gap. And that brings us to the cornerstone of our whole model, the sinusoidally distributed winding. See, in an ideal machine, the conductors aren't just thrown in there randomly. No way. They are arranged with a very specific density pattern, and the whole point is to produce that perfectly sinusoidal magnetic field. By assuming our machine is ideal, we can create a model that is both elegant and, you'll see, incredibly accurate.
So, how does this actually work? Let's break it down, starting with Section 2, a single phase. To really get the entire machine, we have to start with its fundamental building block. So for now, let's just forget everything else and focus exclusively on the Phase A winding. So take a look at this cross-section of that Phase A winding. We've defined its magnetic axis as our 0-degree reference, our starting point. Now look at that equation, NS of theta. This is the secret sauce. It describes the conductor density as a function of the angle theta. To get that ideal field we're after, the physical density of the wires in the slots has to follow a sine function. I love this slide because it makes that abstract equation totally tangible. Imagine we could just slice open the stator and unroll it flat. This is exactly what the physical conductor density would look like. You can literally see the sinusoidal shape. It peaks at 90 degrees, or pi over 2, and then you see the return path for the current on the exact opposite side. So what happens when we pass a current, IA, through this winding? Well, it kicks off a direct chain reaction. The current creates a magnetic field intensity, H. Now, assuming we have a linear magnetic material, this produces a proportional flux density, B, and all of this results in the magnetomotive force, F. The critical thing to remember here is that all these resulting fields are going to share the same spatial shape, which, as we're about to see, is a cosine wave. And this right here, this is probably the most important insight so far. There is a 90-degree spatial shift between the winding and the field it creates. Let that sink in for a second. We physically arrange the conductors in a sine distribution, specifically to produce a magnetic field that's shaped like a cosine wave. This isn't an accident. It's a fundamental design principle of the entire machine. And this image does a fantastic job of showing what that cosine-shaped field looks like. Now, for a single phase with AC current, the field does not rotate. It's a standing wave. Its spatial shape is fixed, always peaking right along that phase A magnetic axis. As the current IA flows back and forth, the amplitude of this wave just grows and shrinks. It pulsates right there in place.
All right, we've totally nailed the single phase. Now for Section 3, where we assemble the complete 3-phase stator. And trust me, this is where the magic really starts to happen. The construction is just beautifully symmetric. We take our Phase A winding and we just replicate it twice. Phase B is identical, but it's physically rotated by 120 electrical degrees. And Phase C is also identical, just rotated by 240 degrees. This precise, symmetrical placement is the entire key to how the machine generates a rotating magnetic field. So on top of the mechanical spacing, we also have to connect the windings electrically. The most common setup is the Y, or star connection. You can see one end of each phase is joined together at a neutral point. Now, since this neutral point usually isn't connected to anything, Kirchhoff's current law gives us a vital constraint. At any single instant in time, the sum of those three phase currents, IA, IB, and IC, has to be zero. And as you would probably expect from all this symmetry, the fields from phases B and C are identical in shape to the one from phase A. They are all cosinusoidal standing waves. The only difference is where they're pointed in space, which is determined by their magnetic axes, peaking at 120 degrees for phase B and 240 for phase C. Okay, so we've got the whole concept down. Let's move on to section 4 and actually put some numbers to this by calculating the stator inductance parameters. This is what's going to let us create a real circuit model. Now, to do this calculation, we have to make two key assumptions. First, the windings are Y-connected, just like we discussed. Second, we have to imagine the rotor is there, but it's electrically inert, like it's been open-circuited. This is a really critical step because it lets us analyze the magnetic properties of the stator all by itself, without any confusing effects from currents that would otherwise be induced in the rotor. Let's start with the self-inductance of a single phase, which we'll call LS. This is actually made of two distinct parts. First, you've got the leakage inductance, LLS. You can think of this as wasted flux. It links its own winding, sure, but it doesn't cross the air gap to do any useful work. The second part is the magnetizing inductance, LM. Now this is the useful flux. This is the stuff that crosses the air gap, linking with the other phases in the rotor to actually make the motor turn. Okay, now this is where it gets really cool. Watch how the machine's geometry directly defines the mutual inductance between phases. So current flows in phase A, right? It produces magnetizing flux along that 0-degree axis. Now, how much of that flux actually links with the phase B winding, which is sitting over at 120 degrees? Well, it's just the projection of the phase A flux vector onto the phase B axis. And that projection is simply scaled by the cosine of the angle between them, the cosine of 120 degrees, which is exactly -1/2. It's that simple. The geometry gives us the answer. Okay, home stretch, final section. Let's assemble all these pieces into our final model, moving from the physical machine to a complete mathematical description. Let's just step back and look at the journey we've been on. We started with a physical squirrel cage and we modeled it as an equivalent three-phase winding. We saw how a sinusoidal conductor distribution creates a cosinusoidal MMF. And we just used the 120-degree geometry of the machine to derive the inductance parameters. In short, we've successfully translated a complex physical object into a clean, neat set of mathematical values. So here's the bottom line. The crucial point is this. We have now successfully created a complete phase variable model for the stator, and this model is defined by just two key parameters, the self-inductance LS and the mutual inductance L mutual. We now have everything we need to write the voltage equations and really begin our dynamic analysis. But this model, while it's perfectly accurate, it can be a little clunky to work with, especially once the rotor starts to move and the inductances become time-varying. So this leads us to a final, forward-looking question. Now that we have this model and these stationary ABC phase quantities, is there some kind of mathematical transformation we can apply to make it dramatically simpler for designing high-performance control systems? The answer is a big yes, and that is the topic for our next explainer.
All right, class, welcome. Have you ever really stopped to think about what's going on inside an electric motor? I mean, these things are literally everywhere, but they work based on these invisible magnetic fields. So today, we are going to peel back all the layers. We're going to build the fundamental equations that bring these incredible machines to life, and we're going to do it right from scratch.
So here's the central question, right? This is the puzzle we have to solve. How do we take something as beautifully simple and rugged as a squirrel cage motor, and then describe its incredibly complex magnetic behavior with mathematics? That's our main challenge today, to build a model that's every bit as elegant as the machine itself. And this brings us to what I like to call the squirrel cage paradox. Just look at it. You've got these simple, uniform, evenly spaced bars on the rotor, yet somehow they all work together to create this perfectly smooth, wave-like magnetic force. How in the world does that happen? Well, to figure it out, we're going to do a little bit of math magic. We're going to mentally swap out that simple squirrel cage for an imaginary wound rotor. Now this little trick, this is the key that unlocks the whole puzzle for us.
Okay, let's get our hands dirty. We're going to start with the absolute most basic component, a single stator phase winding. If we can really nail this down, truly understand how it works, the rest of the machine is just going to fall right into place.
Think about it like this. If you want a perfectly smooth, sine wave-shaped magnetic field in the air gap, You have to arrange the wires in a very, very specific way. See, they're not just evenly spaced. They're bunched up in some places and spread out in others, and they follow the pattern of a sine wave perfectly. That equation you see, the one for ns of theta, that's just the mathematical blueprint for that exact pattern.
And check out this graph. It's the perfect picture of what we were just talking about. You can literally see how the wires, represented by those little dots, are clustered together. The highest concentration is right there at the 90-degree mark, or pi over 2. And then on the other side, you've got the return path, carrying that current in the opposite direction. It's really like a beautifully choreographed dance of wires, all to create one perfect magnetic field.
Okay, so we've got our winding all designed and in place. Now for the really fun part. Let's pump some current through it and see what happens to the magnetic field. So, we send a current, we'll call it IA, through that winding. That creates a magnetic field intensity, H, which in turn creates a flux density, B. But here's the really interesting twist. Even though we arrange the wires in a sine wave pattern, the resulting magnetic field, which you can see in that final equation for F, is actually a cosine wave. It's shifted by 90 degrees. It's a subtle detail, but it's an incredibly important one that comes straight from the physics.
So what did we just create? We've made what's called a pulsating standing wave. Imagine a guitar string vibrating up and down. Its shape is fixed, right? But the intensity of that vibration changes. That is exactly what's happening here with our magnetic field. Its cosine shape is locked in space, always peaking right along the phasomagnetic axis. But its strength, it just pulses up and down with the AC current.
So we've mastered the single phase, we get it. Now let's take that knowledge to the next level and see how this all comes together in a real-world three-phase machine.
The principle here is actually pretty simple, and it's just so elegant. We take our perfectly designed phase A winding, and we just make two more identical copies of it. Then, we physically rotate the phase B winding by 120 electrical degrees and phase C by another 120. It's this beautiful, perfect symmetry that makes three-phase motors so incredibly powerful and smooth.
Now, of course, we need to connect these three windings together. We do that in what's called a Y, or a star, configuration. I want you to imagine three ropes tied together at a single point in the middle. That point is our neutral. And because that point isn't connected to anything else, the forces in the ropes, they have to perfectly balance out. Well, it's the same exact thing with the currents in our windings. Kirchhoff's current law tells us that at any given moment, they have to add up to 0.
And here it is, the beautiful result of all that symmetry. Each phase is producing a magnetic field that's identical in shape to the others, but they're all pointing in different directions, exactly 120 degrees apart. It's kind of like having three dancers, right? They're all performing the exact same move, but they're facing in different directions to cover the entire stage. So, we've got the physics down, we understand the geometry, now it's time to start speaking the native language of electric machines, and that's the language of inductance. This is how we're going to quantify everything we've just built. Okay, before we start crunching the numbers, let's set some ground rules just to make our lives a little easier. First, we're going to assume the windings are Y-connected, which, we just talked about. And for now, we're going to imagine the rotor is just sitting there, not doing anything electrically. This lets us focus purely on what's happening in the stator. So when we talk about the self-inductance of a single phase, this LS, we're really talking about two different things combined. First up, you've got the leakage inductance, LLS. Think of this as the magnetic field that just kind of hangs around its own wire and doesn't really do much useful work. But then you have the magnetizing inductance, LM. Now this is the good stuff. This is the powerful magnetic field that actually crosses the air gap to interact with everything else in the machine. Now this is where it gets really cool. The mutual inductance, that's how the magnetic field from one phase affects the others. It's all about geometry. It's like casting a shadow. The amount of magnetic shadow that phase A casts on phase B depends entirely on the angle between them. And the math for that projection is simply the cosine of the angle, which we know is 120 degrees. That directly leads to that -1/2 term you see in the equation. It's just a beautiful, direct link between the physical layout of the machine and its electrical parameters.
And there we have it. We've done it. We've taken the machine apart piece by piece, we've understood the physics, the geometry, and the math, and now we have everything we need to put it all back together into one complete mathematical model. This one slide really captures our entire journey today. We started with the physical reality of the squirrel cage. We used a clever trick to model it, which led us to the symmetrical geometry of the three phases.
And then that geometry directly gave us the mathematical inductance parameters that define the entire system. It's just an incredible example of how we use abstract mathematics to understand and control the physical world.
So, we've built this incredibly detailed and accurate model. It works, it's perfect, but it's also pretty complicated, especially when things start moving and spinning. So what if I told you there's a much, much simpler way to look at this whole system, a kind of secret perspective that unlocks a whole new level of performance and control? Well, that is exactly what we'll be exploring in our next explainer.
All right, welcome everyone. Today, we're diving straight into Chapter 2 of Mohan's Advanced Electric Drives. Our goal is to really build a solid, intuitive model of the induction machine, right from the ground up.
So here's our game plan. We'll start with the what if, the perfect ideal AC machine. Then we'll get our hands dirty and look at the anatomy of a single winding. From there, we'll see how we scale that up to the full three-phase stator, and then we'll introduce a really elegant tool, the space vector, and tie it all together by asking why this framework is so absolutely critical for modern drive control.
You know, this is the fundamental challenge we're tackling. We have this physical thing, a chunk of steel and copper windings that spins. How on earth do we translate that physical reality into a set of equations, a mathematical model that lets us predict its behavior and, more importantly, control it with precision?
Okay, so let's start at the beginning, with the ideal. Before we get lost in the weeds of currents and windings, we've got to ask, what is the perfect world scenario? What are we actually trying to achieve inside this AC machine?
And this quote from the textbook really hits the nail on the head. The entire design goal is to arrange the wires, the conductors, so that their density changes like a sine wave as you go around the air gap. And why do we do that? Because a winding built that way creates a perfectly smooth, sinusoidally distributed magnetic field. And that right there is the secret sauce for efficient, smooth operation.
So, we know the goal is this perfect sine wave field. Now let's see how a single-phase winding is actually put together to get as close as we can to that ideal.
Take a look at this diagram from the book. This is our fundamental building block, the winding for phase A. Now notice, it's not just one big coil of wire. The conductors are strategically placed all around the stator, and this placement is intentional. It's designed to create what we call a magnetic axis, which for our phase A we're defining as being right at the 0-degree mark.
And this brings us to a more formal definition. So when we say sinusoidally distributed winding, we don't mean the wire itself is wavy. It means the density, how many wires are packed into each little slice of angle, varies like a sine wave around the stator. This is how we physically sculpt the magnetic field. And of course there's math for that. This is equation 2-1 from the text. All it's really saying is that our conductor density, Ns, is a sine function of the angle theta. And if you think about it, that makes perfect sense. The density is 0 right on the magnetic axis, and it peaks 90 degrees away from it, which is exactly what we need to shape the field properly.
And here is the beautiful result of all that careful design. When you pump a current, Ia, through that winding, the magnetic field intensity you get, H sub A, has a perfect cosinusoidal shape. It peaks right along the winding's magnetic axis at theta equals 0, exactly where we wanted it. This is that crucial link between the physical construction and the magnetic result.
Okay, so we've nailed down how to make a great single-phase winding, but induction motors are almost always three-phase. So the next logical step is to just take our perfect building block and replicate it.
And here in Figure 2-2, you can see exactly how it's done physically. We just take 3 of those windings we designed, one for phase A, one for B, and one for C, and we install them in the stator so that their magnetic axes are physically shifted by 120 degrees from one another. So phase A is at 0, B is at 120, and C is at 240 degrees.
Now, this is an important distinction. The last slide showed the physical arrangement. This slide, 2.2b, shows the electrical connection. You can see the 3 windings are all tied together in what we call a Y or star configuration. This is the complete electrical circuit that we're going to hook our power up to.
The really key takeaway here is that the windings for B and C are basically clones of A. They work exactly the same way. When current flows through them, they each produce that same beautiful cosinusoidal magnetic field. The only difference is where their fields are pointing in space. They peak along their own magnetic axes at 120 and 240 degrees.
So let's just pause and think about what we've got now. We have 3 separate currents, all changing with time, creating 3 separate magnetic fields, all oriented in different directions. You can probably imagine that trying to keep track of how all those things interact at once would get mathematically messy and fast. This leads us to a really brilliant question. What if, instead of tracking three messy quantities, what if we could just represent the total magnetic effect of all three phases with one single, clean, rotating vector? And the answer is the space vector. This is a complete game changer for our analysis. It's a mathematical tool that lets us combine the effects of all three phases into one single entity. This one vector tells us both the magnitude and the spatial direction of the net magnetic field at any given moment in time. It's incredibly elegant.
And the math behind it is just simple vector addition. The total magnetomotive force, or MMF, of the stator is just the vector sum of the individual MMFs from each phase. Look how cleanly that combines three separate things into one simple variable.
So why did we go through all this trouble? Starting from conductor density, building up to windings, and now introducing this abstract idea of space vectors. Why does this whole framework matter so much?
Let's just quickly recap the big ideas. We start with the ideal, using specially designed windings to get a perfect sine wave magnetic field. We then use three of these, spaced 120 degrees apart, to create a rotating field. To make sense of that complexity, we use the magic of space vectors, which boils the whole three-phase system down to a single vector. And the bottom line? This entire model gives us that crucial link between the currents we can control and the magnetic field inside the machine that actually produce the torque.
Now, the most important point is that everything we've built here, this whole analysis in what we call phase quantities, is really just a necessary stepping stone. It gives us the physical intuition and the mathematical groundwork for the next level, for an even more powerful technique.
So, what's next on the horizon? The DQW winding analysis. See, this phase quantity model, as accurate as it is, still has some complexities, because things like inductance can change as the rotor spins. The next evolution is to transform this entire system into a rotating reference frame, the DQ model. This makes the dynamic analysis worlds simpler, and it is the absolute bedrock of modern, high-performance motor control.